So these are the laws of logs. Basically, they are rules that allow us to manipulate logs. If you want to add 2 logs, you get a log of a product. Subtract 2 logs, you get a single log of a division. And if you multiply a log by a number, you get the log of its power. And we actually tend to use the rules going from right to left. And these get used sometimes. So there's things we just need to know, and they it's like a little tool bag. You bring it out and you use it when you need to. And then a lot of questions you won't need to. Here is a reminder of what the derivative of a log is, of a natural log at least. It's unusually 1 over x. And if you remember, I proved it. And a couple of hints. If you want to differentiate a function with a log in it, first thing you might want to do is to see if you can simplify it first before you differentiate. And second little helper, many derivatives of log functions use the chain rule. Okay, so we're really going to get lots of practice at doing derivatives with logs in them. Right, the natural log of this guy. This is the log of something. So you differentiate it, you get 1 over the something times the derivative of the something. And then you kind of try and make it look pretty, but the chances are you won't get very much out of it. There's your answer. Right. 30-second kind of question, not a lot happening. This guy has a log in it. It's a log inside the sine function, kind of weird, but it's allowed. So this is a chain rule, right? It's a function of a function. A little bit more going on here. The derivative of the sine of something is the cosine of that something times the derivative of that something. So it's the cosine of 3 log x's. And if you differentiate 3 log x's, you get 3 over x. And you want to make it at least as pretty as you can. Probably look something like that. So that would be kind of the first level of derivatives. Functions that have logs in them, but you didn't need to do anything to them, and you typically use the chain rule. Now, this fella here is going to incorporate that guy. It's a bit like my rule, just because you can doesn't mean you should. Now, I could certainly just differentiate that without changing things, but if I did that, I would be just making my life more awkward than I need to. So what I'm going to do is I am going to have a look, at least have a look to see if you can simplify it. 1 over x to the 5 is that guy. You agree? 1 over x to 5 is a negative 5th power. And then I'm going to notice that that guy can be used with rule 3 and can be written as that guy. So all I've done right now is take the original log function and rewrote it like this guy. Now this guy's dead easy to differentiate. And we're finished. Do you see how easy the derivative was after I spent a little bit of time simplifying it? It's much easier to differentiate that than to try and do that. If you tried to do that as is, wouldn't that be a chain rule, right? It'd be a 1 over this ugly guy times the derivative of this ugly guy. Can you imagine how many fractional powers would be going on there and trying to keep, I mean, eventually it would simplify that, but can you imagine how much more difficult it would be just leaving things alone? So when logs are involved, have a little look to see if there's something you could do. In that same vein then, suppose I had to differentiate that thing. Now, if I left it alone, this thing would take that entire page to do. I mean, technically I could do it. it be a chain rule inside a chain rule with a product rule going on, right? Which I prefer not to do unless I absolutely have to. So I need to figure out how to use these three guys, but typically going that way. Okay. If you think of this as the A times and think of this as the B, isn't this just a log of something times something? Which means I should be able to split it as this guy plus the log of this guy. So far, so good. Now, if you think of this as like A to the power of n and B to the power of n, isn't this that guy? And so I can rewrite this fella more like this guy. So the natural log of 3x plus 10 to the power of 10 can be written as 10 times the natural log of x of 3 plus x plus 1. And this fella, 8 times the natural log of 2x minus 1. So after 2 lines, I have taken the original log, which is really ridiculously difficult if you try to differentiate it untouched, to a much nicer equivalent expression. I'm trying to sell this idea that this is helpful, right? You can take something and make it nicer before you differentiate it. Right, this fella here is basically just going to be a very minor chain rule. So 10 times the log of something is 10 over that something times the derivative of 3x plus 1, which is that guy. And this fella is 8 times the log of something. So it's 1 over that something times, I don't know why I put that there, times the derivative of 2. Right? So 8 over something times the derivative of something. So what do I get? I get 30 of this guy plus 16 of this guy. And I would just call that quits. Are we good with that one? Right. Here's another one where you should do algebra first. This is like question 5 in your homework. And the function is the natural log of x e to the negative 5x. And I certainly wouldn't want to differentiate that untouched. I mean, it would be a chain rule with a product rule with a little baby chain rule at the end floating around. An awful lot of Russian dolls going on in that question. So I want to avoid that. Any idea how I could split this?
Using the first log, AB.
Great. Two things multiplied can become 2 logs added. Great. Can you imagine you could get a division question where it would be 2 logs divided become 2 logs subtracted, right? So multiplication turns into 2 logs being added. A division, right, a log of a division would turn into 2 logs being subtracted. Now that's better, but I can do a little bit more. But this one requires you remembering something to do with logs and exponentials and how they interact with each other. Do you know what the natural log of e to the power of something is? Because there's a kind of cancelling going on. What's the natural log of e to the power of negative 5x?
Negative 5x.
Nailed it, yes. Now, God, who knows when you did that? It's one of those little pieces of information that gets used a few times in you know, they move on to something else, but it is in there. Now, all I've done is take ugly guy and make it simpler. Now I can differentiate. That guy is 1 over x, and that guy's take away 5. So do you see how simple the derivative process was because of the hard work that we put in at the start to make it look pretty? This one is like question 6. I really don't want to have anything to do with trying to differentiate that guy. Oh God, that would be horrible if you had to do it as a chain rule inside a chain rule inside a chain rule. I mean, I could do it, I guess, but I really would choose not to. It's a little bit less obvious how I can fix it using one of these rules, but I can fix this, I can simplify it. Any suggestions for a better way to write this that might help us? Another way to write a square root. I guess that's what I'm asking.
The fractional power.
Yeah. Now, if I write it as a fractional power, do you see that there's a guy over here that I can now use? Wouldn't that become 1/2 a natural log? That's it. That's as good as I can do it, right? So now I'll differentiate. Okay, if you want to differentiate 1/2 the log of something, you get 1/2, 1 over that something, times the derivative of that something. And those two guys kind of cancel out, and you get actually a very pretty answer. Not only was it a pretty answer, it wasn't that hard to do. This one I like a lot. I like this question. When I saw it, I thought, oh, what a cool question. But I want to make it pretty. I want to simplify it before I differentiate it. And superficially, it looks like there's nothing you can do. But you have to look a bit harder because there is something you can do.
Could you factor out the e to the x?
I like your thinking. Yes, you can. Where do you think this is going next then?
You can use rule number 1 with the products, and you can separate it into 2 lines or logarithms.
I like your thinking. Tiny little bit and we're done here. Is there anything else going on here that could be simplified?
X can be moved out in front of the first one for the X.
Well, and eventually just get X. You want to cut out the middle one.
Yeah.
Would you agree that this is a much easier function to differentiate than that one? Can you see the amount of work you'd have to do if you left it alone? So derivative is 1. Technically, this is a chain rule. It's 1 over the something times the derivative of the something, which is just 1, so it doesn't really change anything. And so there's your answer. I mean, it's a kind of cool question. I like questions that look horrible but turn nice. It's a nice question. Well, this is kind of the end of the road for that process of making, see if you can make things simpler before you do it. Of course, since it is the end, it's got to be it's got to be a horror movie ugly, right? That's pretty horror movie ugly, right? You know that you do not want to differentiate that right now. Can you imagine how many chain rules inside chain rules? God, there's a quotient rule happening somewhere in there, isn't there? Eventually. And square roots and half powers. And God, if you could keep all those balls juggled in there, you'd be a better man than I am. I do not want to do that. So we will not do that. We will change it into something prettier and easier. So start the ball rolling. What should I do?
The square root to the power of a half.
Good start. Where am I off to now?
When you use log rule 2, does it put a half in front of both logarithms?
Well, it puts a half under this log right now. And later on, what you talked about is going to be yes. But right now, I'll just take care of the half. I think we're going to end up where you think we're going to end up, Robin. It's just I'm maybe taking a slightly different road. We got a log of two things, right, being divided. And we can work on that, can't we? What will I do with that?
Subtracted.
I agreed. And I would distribute those two halves. I think that's a little bit easier to deal with. Is that where you thought you might end up, Robin? Because that's what I thought you thought.
Yeah, that's where I was.
Yeah, that's it. You just took a slightly different route. I think you might have separated them out as halves and then brought them out separately, but you get the same place. So let's, in a few moments, do the derivative. But that was the original. And would you agree these are much easier to deal with? Right. So it's a half the log of something. So if you want to differentiate the half a log of something, it's a half 1 over that something times the derivative of that something. This one here, minus a half 1 over something times the derivative of that something. The half and the 8 get me a 4. The negative 8 and the negative a half get me a plus 4. And we are finished. So those 3 laws of logs have came in really handy, haven't they? At least for these ugly ones. Now I'm going to show you a technique called logarithmic differentiation. Now, logarithmic differentiation, when you see it in operation, combines two different things that we've been doing. One of them is dealing with logs and simplifying them before we differentiate them. And the other thing is implicit differentiation. And we're going to put those processes together to help us find derivatives of weird powers. Now, let me tell you what it's not. It's not the power rule. So you don't multiply by the power and reduce it by 1. I wish it was. It would make life 10 times easier than it's going to be. But that is not the derivative of 4 to the power of x. It is not a power rule. Well, maybe the answer is just 4 to the x, because the derivative of e to the x is e to the x. So maybe the derivative of 4 to the power of x is just 4 to the power of x. That would be nice, but it's not. So I'm telling you what it's not. When you find out what its derivative is equal to, it's kind of ugly. It's not as clean as e to the x gets you e to the x. I like that one. So how does logarithmic differentiation work? Well, it happens a lot in mathematics that you're given a puzzle, right? The first guy in the world had to figure out how to do that, right? There's always a first for everything. And, you know, I'm guessing the mathematician's looking at that, and he's looked at all the things that other people have done. And he said, well, I saw this cool thing called implicit differentiation. I wonder if I could use that. And I've done so many of these log things, maybe I could use that. And he probably played about with it, right? Or she probably played about with it. And they came up with this idea. First line is you take the natural log of both sides. So this is the process called logarithmic differentiation. Step 1. Take the log of both sides, the natural log of both sides. Okay, can do that. Simplify it, because there's always going to be a simplify. That's step 2. Oh, by the way, isn't the natural log of 4 just an ugly decimal? I don't know. I'll put this in. I don't know if this helps or actually makes it worse looking. It's the same thing as like 3x, right? But it's going to be like 2.8977x, right? It's just a multiple of x, just an ugly number. Step 3, differentiate. Well, if you differentiate the natural log of 4x, don't you just get the natural log of 4? Like 5x gets you 5 and 1.2x gets you 1.2. Great. Now, implicit differentiation is happening here. If you differentiate the natural log of y, don't you get 1 over y times dy by dx? And that's step 3. Remember, when you differentiate anything with a y, you finish with a dy by dx. You know, so y cubed gets you 3y squared dy by dx, and log y would get you 1 over y times dy by dx. I mean, that's what's happening. Where do you think they went next in this process? Remember, the goal is to find the derivative dy by dx. Where do you think they went next?
Multiply both sides by y.
Correct. And that is the answer, but it's not the answer I want. Don't I want the answer to have x's in it? I don't want to have an answer with a y in it. That's no use to me. I don't want y's, I want x's, right? I want derivatives with x's. So what do?
You take the value from the top, which in this case is 4 to the x.
And we have now found the derivative of 4 to the power of x. It's actually just the natural log of 4, right, times 4 to the power of x. So why does e to the x work? Well, if I use this rule, wouldn't the derivative of e to the x be the natural log of e times e to the x? Great. And what number is the natural log of the number e? 1, right? In fact, do you know why we got e? You know, e is just 2.7128. They wanted to find a number that had that property, that its derivative was the same as itself, because they thought if we could find a function, right, a base, right, e is what it called, right, but some base where when you differentiated it, you got the same guy you started with, that would be a very useful base to write formula in, because it would make the manipulation 10 times easier than if you use 10 to the x or any of the other, you know, 2 to the x would be another one that's quite common. Cool. So let's go crazy. X to the power of x. Good grief. Can you imagine what that would look like? And you know, you can't use a power rule because it doesn't work, and you can't use this one. What you can use is logarithmic differentiation. So I'll take the log of both sides. I'll pull this guy out. And we're now looking at that fella. Okay, now I'll differentiate. 1 over y dy by dx. What method am I going to use to differentiate x times log x? How am I going to differentiate x times log x?
F dash g plus f g dash.
Yep, going to use the product rule. So it's going to be 1 times the log of x plus x times the derivative of log x, and end up with that guy. Then I'll multiply. You kind of finish the same way each time. You then multiply both sides by y, and then you finish by replacing the y by its original value. There. Well, when you look at that original function, and now you look at what its derivative, would you agree that you probably wouldn't have guessed that? Right. And when you do unusual powers, right, x to the x, 4 to the x, can you see that you're going to have to deal with unpredictable answers? It's not something you could have a good guess at, and you might get lucky and guess it. 9 times out of 10, if I try to guess, I just get it wrong, essentially. I might have guessed the log bit, and that makes sense because of, you know, if I use that as my guide, I might have thought, oh, this is going to be just log x, x is x. Can you see it might make sense? But I wouldn't have guessed that you needed an extra +1, right? That doesn't seem intuitive. That's why you can't always trust patterns. You know, you think you see a pattern, and then, darn it, that one doesn't work. Okay, let's see where we're off to next. Well, I guess for completeness sake, I should do a log that has a product in it and a log that has a quotient rule in it, so I'll do that. So we're going to do x squared natural log of x. So we've left special guys now, right? We're back to just, differentiating things with logs in them. If I wanted to do this guy's derivative, and would you agree it would be a product rule again? And derivative of that guy is 2x, leave that alone. That's x squared, the derivative is that. Looks like you got what? 2x natural log of x plus x. Hasn't happened much today because there wasn't really any possibility of doing it. But shouldn't we do some style points if you can see it? So I'll pull out a common factor AX here. So the kind of questions I'm doing right now are really a bit more standard, right? Here's an example of a quotient rule that has a log in it somewhere. Now, in these questions here, I did not employ this, right? There's nothing really algebraically you could do to this to make it any better, or for the matter, this one. If I call this F and I call this G, I do have a quotient rule that I can use. And you differentiate this guy, you get 1 over x times that fella. Take away the natural log of x times the derivative of that guy. And it's going to be x squared plus 1 squared. Ugh, ugly. Distribute that, you get an x, you get a 1 over x, and you get that guy. The reason why I was growling there is style points. We don't like fractions in fractions, right? We just don't like 1 over x's in a fraction. I mean, I was happy with these two guys. I wish that guy wasn't there, in which case I'd be finished, but it is there. And I can't do the ostrich thing of pretending it isn't. If I can't see it, it's not there. I have to fix it. How do you fix that ugly fraction so that the 1 over x is no longer present?
Can't you change it to being a line of x? Oh, maybe.
Multiply by a special version of 1.
How about multiply by a special version of 1? And what does that get me? Gets me an x squared, a 1, a minus 2x squared log x, and it gets me that guy. Yeah, I'm happy now. Now, I'm not sure what, Kelsey, was it you that was suggesting? Is that not the right way to go? Are you okay? Right. Yeah.
I was just moving ahead and got ahead of myself, saw the pattern, or like the 1 over x, and automatically thought line, changed it real quick.
Gotcha. Yeah. Yeah, well, it finished okay. I wouldn't say I was particularly happy with it, but it was. I guess I should do a chain rule inside a chain rule. I just thought of that because I haven't done that. So let's do the log of an x plus a log of x. Now, definitely a chain rule. That's got a plus there, so I'm not going to be able to use any algebra. And, sometimes you can't avoid it. Sometimes you just have to do the ugly one because there isn't a way of making it nice. So its derivative It's a log of something, so it's 1 over something times the derivative of the something. When I think that something is complicated, I tend to write this line down. So it's now going to be 1 over this guy times, well, the derivative of x is 1, and the derivative of this guy is 1 over x. And I am looking at this fella. But at least this time, we have a cure. And isn't it the same cure I used a few moments ago? And what am I talking about? I'm talking about getting rid of that 1 over x. You see that? Ugly guy. Multiply by a special version of 1. Now what we've got here is the best version of the derivative that we can. It's factored, it looks like the original, right? It's got all the features. When I look at this guy, I notice a couple of very interesting things to me. Would you agree that when x is allegedly -1, this derivative could be 0? Could be, and I've phrased it in a very specific way. When x is equal to 0, would you agree there's bad things happening? So I can look at this function and I can look for what are called critical numbers. Critical numbers are places where bad things happen, virtually, you know, vertical asymptotes or vertical tangent lines. Zeros are nice things, so, you know, critical numbers can be nice things as well. I don't think I need to. If you find y dashed, do you all know how to find y double dashed? Don't you just differentiate your answer? So if I was going to do it to this, which I'm not, because it'd be extremely ugly to do, but wouldn't the second derivative be a quotient rule on this guy? It'd actually be easier to do a second derivative on this one. You just get -1 over x squared. So let's do find the equation of a tangent line, right? It's a pretty standard thing that they ask. Try to find one. Ah, perfect. We have a function, which is this fella, and we're being asked to find the equation of the tangent line at the point 4, 0. So this is going to be our last question for today. Well, first thing I'm going to do is find the derivative. So it's a log of something, so it's 1 over something, followed by the derivative of that something. So it's what? 2x minus 4 over the guy. That's good. And I'm going to find the slope of the tangent line by evaluating the derivative at 4. So it's 2 lots of 4, take away 4, over a 4 squared, take away 4 lots of 4 plus 1, and the slope, by coincidence, is 4. And then I use the point slope equation, which is that guy. Y take away 0, 4, x take away 4, and this would become that guy. Are we getting used to the find the equation of the tangent line that they tend to tag on at the end of many of the things we do? It's got a very straightforward process, right? Find a derivative, evaluate it at this x coordinate. That gets me the slope. Point slope equation where you plug and chug, make it look pretty. I don't have time for it, so I'm going to pretend I did. Can you imagine I plugged that into the calculator and it looked like that? And this was the point. Wouldn't that be y equals 4x minus 16 kind of thing? You know, I know that picture's totally wrong, but you could check it. Okay, say hi and bye-bye.